Okay, welcome to my Master of Skies weather briefing show. I'm Lionel Perro. It's been quite a while since I've recorded one of these shows. Had a quite busy fall and winter so far, and so just haven't had the time to actually record any of these. Hopefully I'll be able to record more shows for you guys in 2026 during the spring and summertime. So in the meantime, what are we going to be talking about today? We're going to be talking about the nor'easter blizzard that just affected the eastern United States on this 22nd, 23rd of February 2026. It was a really deep mid-level cyclone that was actually undergone what we call bombogenesis, which is when a mid-level low-level pressure system actually has a central pressure that drops more than 24 millibars in 24 hours. And actually this storm actually had a central pressure that dropped about 30 to 33 millibars in 24 hours. So a very intense mid-level cyclone. And so we're going to be looking at a little bit the causes for this very rapid deepening for this storm, drawing upon some of the educational material that you may have already followed or purchased with some of my weather courses regarding weather forecasting. And so I'm going to be drawing upon some satellite and radar imagery. We're going to be looking also at numerical weather model fields to try to explain a little bit what was going on with this very intense storm. So that being said, let's take a look a little bit at this short video here. You guys might have seen some of this footage already in the media where you see this very intense snow with the wind affecting New York City and most of the eastern seaboard with these very heavy snowfall rates and strong winds, really creating blizzard-like conditions with really important snowfall accumulations. So that with that being said, let's take a look at what was going on here. So everything here in that's drawn in orange is actually the blizzard warnings that were in effect ahead of this storm, drawing into Delaware, Maryland, and all of New Jersey, basically, Long Island, southern New York State, Connecticut, Massachusetts, and the Boston area out to Cape Cod. And so we were really expecting really intense weather conditions with regards to the snow and wind. So here is an interesting satellite image of what the storm actually looked like as it was exploding off the coast of New England. And what's really interesting here is you can really see many features with regards to this cyclone. First of all, you could see the the center of this low pressure system, which is really located right here. And then you have this long stretch of clouds, which is delineating the cold front here with some convective elements also along the line, since this cold front was actually pushing over the Gulf Stream. And so you really have some maritime tropical air over this region with southerly winds. And so you had some instability causing some thunderstorm activity. And you even see what we call a rope cloud here, which is sort of the gust front from the convective activity all along the front here. And you can really see that clearly on this visible satellite imagery. What you also see is this sort of convective, these small convective lines, which represent really these shallow cumulus clouds that are caused by cold air off the land coming over the warm Gulf Stream waters, creating sort of like what you see sometimes with the lake effect snows over the Great Lakes, but it's actually really continental polar air flowing over the very warm Gulf Stream waters and basically convecting and creating these cellular-like clouds. And if you were to look at the radar, you would also see some snow squall bands under those clouds as this cold air really was being blown over this warm water. You also see here the warm front here, where ahead of the warm front near the surface, you have really cool air, and then you have the clouds being lifted over that cold air and creating all this cloudy warm front clouds and precipitation. You could also see some convective elements along the triple point just ahead of the occlusion, representing some convective thunderstorms here going on. And then you have the basically the cold conveyor belt wrapping around the center of the low, representing cooler air near the surface being wrapped around the occluded part of the cyclone, where you're getting most of the snow that was affecting the northeast of the United States. And you could also see sort of an eye. It almost looks like a hurricane, but it's really not. This is what we call a cold core weather system, since it draws its energy on temperature differences, what we call in meteorological jargon the baroclinicity. And so this is not a warm core system like a hurricane, even though what you have here is really some cold air over sort of the relatively warm water. And so you're getting sort of shallow convective elements that's really releasing latent heat. And so you're basically sort of getting some of a similar phenomena as what occurs in polar lows, as they we have cold air over sort of relatively warm water. And so you sort of almost get sort of an eye feature with this low pressure system. Also, typically ahead of this cold front, you'll have the warm conveyor belt, which will usually sort of injects warmer air up ahead and over the warm front. You have the cold conveyor belt at low levels that's wrapping around the occlusion, and then you have the dry conveyor belt that usually brings in drier air into behind the cold front and south of the occlusion. And sometimes when that happens, when you have this dry air coming from aloft and then sort of subsiding downwards around this low here, you can get what we call sometimes a sting jet, where you have evaporational cooling that accelerates the wind or with already tight pressure gradient, since this cyclone had a central pressure at this time of about 970 millibars or 970 hectopascals. And so this tight pressure gradient with this evaporational cooling that goes on sometimes around these very intense mid-latitude cyclones, you can really create really strong winds just south of this occlusion. And so that's typically one of the hazards with these type of storms, but you basically have a strong wind field all around this center of circulation as this low pressure system was bottoming out really quickly as it moved offshore. So we're going to be looking at that in a little bit more detail. If we keep going, you could also see a nice loop of this storm on satellite imagery, where you have a combination of both infrared and visible satellite imagery from the GOES-19 geostationary satellite. Here's the infrared imagery, where you can see all this moisture being wrapped around this occlusion, where you have a northeast wind in continental polar air and maritime polar air, bringing all that moisture and that snow over the northeast corner of the United States. So really neat animation. And you could also take a look at other products, such as this multispectral image using the Airmass product from GOES-19, where you basically see other features as well. This sort of red area here represents the center of the cyclone, which is usually composed of mostly stratospheric air, as you have subsiding dry air being sucked into the cyclone from aloft and creating this sort of these sort of red tones that are enhanced with this sort of satellite imagery. But it helps you really identify the source of the air masses, where the green represents more sort of maritime and tropical air masses, and where the blue here shades represent more polar air masses. And so you can really see the distinct differences between cold air, warm air, and dry air, and how that interplay comes in with this developing cyclone. What you also see are these little dots that are popping up, and that's related to the lightning activity from the lightning imager on the satellite. And you could see some of this convective activity along the warm front and along the cold front and the occluded front. Basically, as we were talking about earlier, you have this warm conveyor belt advecting maritime tropical air just ahead of the cold front. And when this air is lifted over both the warm front and the cold front, you can get elevated convection and some thunderstorm activity embedded in the occlusion, which sometimes actually creates what we call thundersnow, where you can actually hear the thunder and see the lightning while it's snowing. And usually when you experience that, that usually means that you have a lot of upward vertical motion, a lot of lift in the atmosphere, coupled with some unstable layers. And that can usually create very intense snowfall rates up to 2 to 3 inches an hour, and sometimes even more. And so when you get thunder snows, you know that you're experiencing a very intense part of the cyclone, and that you can expect very intense snowfall rates during those times. Okay, and moving along, here's another shot here, this time from water vapor satellite imagery, where basically the yellow tones represent drier air, and it's really a visual representation of this dry conveyor belt wrapping around the cyclone as it deepens off the eastern seaboard. And so this dry air comes into play also with the creation of the sting jet just south of the center of low pressure, and you can see it's actually pushing against the cold front, and helps also steepen the lapse rates, which also tends to help some of this elevated convection occurring, as we were seeing not too far from the Cape Cod region. So all these different types of satellite imagery can be very helpful when trying to forecast and trying to understand what's actually going on with these type of storms. Now we can also take a look at let's take a look at some of the radar imagery. Here's a little radar loop of some of the occluded part of the precipitation from the night from Sunday to Monday morning, overnight Sunday, and you can see some of these pretty intense reflectivity values, even up to 35 to 40 dBz. And usually when you get those kind of intense bands in cold air, you can almost be assured that you're really getting intense snowfall rates under those regions. And so this was part of the intense part of the cyclone as the occlusion was really wrapping itself around over the New York metropolitan area and most of New Jersey. And if you take a look at sort of a composite shot, you could see also with the blue tones representing what was snowing, you could see the wide spread of the snow all the way from Boston down to Washington, D.C. And that was part of the cyclone as it was really occluding and bottoming out really quickly in terms of the pressures and causing a lot of snow in this really intense nor'easter snowstorm. Okay, so moving along, we're going to take a look at also an important feature also for you guys that are familiar with the Fibonacci spiral and the Fibonacci sequence. A lot of times you get this naturally occurring sort of configuration in nature, including in low pressure systems, where you can see how well the Fibonacci spiral actually sort of mimics the configuration of this low pressure system as this nor'easter was actually bombing out over the east coast of the U.S. Okay, so let's now take a look a little bit at some of the weather maps and how things were looking. So these were the forecast maps from Sunday morning as the low pressure system was still over Georgia at 1,013 millibars or 1,013 hectopascals. And you can see, you'll see the evolution of this low as time moves on, as it will slide off the coast and then really deepen really quickly off Cape Hatteras as it moves off to the northeast. And you can see as I move this along, hopefully this will work. Here we go. You can see that as time moves on, you can see it starts to deepen off the coast at 1,004, and then within 24 hours it goes from about 1,000 millibars all the way down, as here's the really deepening part of the cyclone, 976, 970 millibars off the coast. These were, of course, forecast pressures that were pretty much verified to a close degree, and you could see how quickly this low pressure actually, the pressure intensified at the center of the cyclone as the winds were really wrapping around pretty violently. This is sort of the surface winds. You could see how strong the winds were blowing. And you can see sort of the representation of the sting jet as it's really exploding outwards and as it moves to the northeast. Now, what's interesting to try to understand here is why did it deepen so quickly? So if we go back to when it was over Georgia, we can take a look at other maps, such as what was going on at the jet stream level. And if you remember from some of the courses I gave regarding upper level weather, that usually the deepening surface cyclones depend on upper level energy. And so here you have a sort of a broad trough here over the central US. And you can see that as time moves on, there's sort of a short wave here embedded in it, and you get sort of a left front quadrant, which is usually quite favorable for upper level lift and surface low pressure development. And you can see how that left front quadrant basically it remains quite stationary right off the coast of New Jersey as the low pressure system at the surface was moving towards the north. And this actually aids the surface low pressure to really bottom out really quickly in terms of pressure when you have this upper level support. So that's part of the reason why this cyclone deepened so quickly, is because you basically had not only an upper level trough that was providing upper level lift, but you also had a left front quadrant of a jet streak really positioned optimally for that surface low pressure to deepen really quickly. And that was the case also if you go down to about 500 millibars, which is about midway through the troposphere. And what you'll see is that you also had sort of a secondary shortwave from the Midwest actually came in and joined the energy further south. And that actually helped deepen the trough and accelerate the winds in that shortwave. And you can see how strong the winds were also with the left front quadrant at the 500 millibars. And so you're really getting a phasing at different levels of energy in this region, which you could see the reflection of that low pressure system extending really quickly up to 500 as well. Now, if we go down even further, let's go to 850, for example, and you can see here a little bit more the transport in the conveyor belts of energy. You could see the sort of warm conveyor belt ahead of the cold front moving upwards, and you can also see where the low pressure at 850 develops. Usually a rule of thumb is that if your 850 low develops to the east of the land masses during these winter storms, you have a higher chance of the remaining snow over the coastal regions, since you're basically in the cold part of the cyclone at low levels. And so you're not really advecting any warm air that would potentially melt the snow into rain. You're really keeping the northeastern seaboard within this northeast flow at all levels, at least during the low levels, which assures that you're going to be keeping a deep layer of cold air near the surface that will sort of prevent any type of snow changing it over the rain. And you can also see how strong those winds are around that 850 low, as that air is also being progressively lifted over the warm front ahead of it, and all this energy packed into this tight storm as it moves over to the northeast. Okay, so what else can I show you here? So that was basically sort of to explain basically why this storm developed so quickly. Another reason, which is usually important to mention, is, these storms are really typical of the eastern seaboard. And what usually happens is that as low pressure systems sort of migrate towards the coast, they basically end up being right over a natural temperature gradient or baroclinic zone. And so this can also almost be seen as a stationary front that is always sort of lingering along the coast in the wintertime, when you usually have cold air over the land and much warmer water over the ocean. And so this is sort of a naturally occurring sort of frontal zone just because of the difference between the ocean temperature and the landmass in winter when you have sort of northwest winds coming in from Canada. And so when you have a low pressure system that sets up over a pre-existing temperature gradient, that will also help low pressure systems deepen quite rapidly, since when the upper level support comes along, then you can really start advecting warm air northwards and then cold air southwards. And this is what these cold core systems thrive on, is temperature differences, whether it be directly linked to the air, but also the underlying ocean has a big influence. And so that's why usually also some of the tracks of these lows basically mimic the trajectory of the Gulf Stream. So that's always important. And all this moisture, of course, this maritime tropical air, as it is lifted over the cold air dome that was in place over the U.S., typically will exacerbate the snowfall totals, as warm air can contain more moisture than cold air. And so when you lift that over cold air, you have the potential of producing huge amounts of snow. And that's really what happened. So what actually happened in terms of these snow totals? This is some of the snow totals that were actually forecast ahead of time, and we were most of the models were forecasting pretty much in the 15 to 30 inch range, and you can see that most of these snow totals were pretty accurate, at least with the last runs right before the storm. And you could see some of the snowfall totals all around by the National Weather Service, and how high the snow totals were being forecasted, anywhere from 18 to 24 inches or even close to 30 inches along the eastern New Jersey coast. This pretty much verified to some extent. Here are some of the snowfall amounts that were actually recorded. And the red areas here are basically 18 to 24 inches. Which is basically 45 to about 60 centimeters of snow in these areas, and the areas in orange were more between 12 and 18 inches, or between 30 and 45 centimeters of snow. So it pretty much verified to what was expected, with, of course, some variations. And, of course, most of Long Island was also very heavily impacted, as was Connecticut, Massachusetts, Rhode Island, with some very intense snowfall totals and very, very strong winds that were gusting up to about 60 to even 70 or 80 miles an hour in these regions. Further out west over New Jersey, the winds weren't as strong, but still qualified as blizzard conditions, as the very strong snowfall rates were coupled with these very strong winds. Okay, so and here are some other snowfall totals that were recorded by the National Weather Service in different regions with regards to some of these storms, as the storm totals came in, and there you go. And as it turns out right now, this is basically what's left of the storm. You can see we're still snowing in Boston as we speak, but the storm is moving towards the northeast, and snow has now stopped over the New York metropolitan area. So there you go. A very intense snowstorm, to say the least. It was one of the most intense snowstorms, blizzards, since about a decade over the New York area. And so very impactful. We'll probably be talking about this storm for some time to come. This is really a region that gets hit by these storms. I'm not going to say on a regular basis. There's a few years where you don't get any snow, but it's certainly a favorable area for these type of occluded cyclones that can produce very heavy snowfall amounts. So there you go. I hope you enjoyed the show, and I hope to talk to you soon in another show that hopefully I can make in the upcoming weeks. Take care and see you next time.